straight beam, and if we choose 2 points, in this case point A and B, and then we seek for the angle between 2 points, so this angle will be equal to area moment below the diagonal, moment per AI. So the angle equal to moment area. The first theorem. And the second theorem, of the tangent at A point equals the moment of the area, equals the moment of the area. Okay, can you understand this statement? Let me see the diagram. Yeah. The first theorem states about the angle between 2 points, and the second one is talk about the vertical deflection. 1 point to consider from another point. Consider from another point. So in this case, deflection, maximum deflection, vertical deflection point A considered from point B, or vice versa, point B considered from point A. And this is will be also equal to moment area below the diagram. Below the diagram. Moment area. Moment. So please focus on this two theorem because it will be basic moment area method. And this is the angle between 2 points. And the last one is the vertical deviation or maximum deflection 1.2 considered from another point. 1 point considered from another point. So how we can apply or implement this method in the problem? This is the procedure for analysis. The first one is the basic procedure for all problem deflection is determine the support reaction. Determine the support reaction. And then we have to draw the diagram of moment per AI. Diagram of moment per AI. Yeah, if the loads concentrated force, so the moment area it will be from line or straight line. But if the load is distributed one, it will create a parabolic or another high order curve. Another high order curve. Plastic curve. Yeah, you can read later. I already put the handout in the classroom. That's where we check the sample problem. And this is the sample problem. Determine the slope of the beam shown and point at point B and C, which is EI is constant. So the material is uniform and the cross section area also uniform. Along with the beam. And the load is concentrated load or concentrated force at point C. Let's see how to solve this problem. Yeah, after we solve the sub-pop reaction, then we can uh, apply the theorem of moment area method. Yeah, this is how, after you get the moment per AI diagram, this is the typical load for concentrated force, typical diagram for concentrated force. Then we can use this moment, the moment area under the curve to get the slope, to get the deflection as well. Yeah, the question is the slope at point B and C. So at point B, here at point C is here. So at point B, we can write the slope of the angle B considered from point A equal to, yeah, the moment area under the curve of uh, there are two parts. The angle point B from point A and the the slope of point B. And also for point C, there are two parts. Actually, both of them is similar. If you mean angle at point B, so equal to point B from point A, the result is similar. Like this, then we can calculate the slope at point B equal the slope at point B considered from point A, B per A, equal to, yeah, this is the moment area. Moment area is the total area below the diagram. The total area below the diagram. So you see here, this is sometimes only we can consider only triangle, and sometimes we have to divide into two area, triangle and rectangular. So this is the rectangular part, as this one is triangular part. So the total is this one. The slope at point B. See the slope at point B. So this is the uh, rectangular per 2 times PL per 2 AI, and then the another part is triangle area. So the total slope equal to this total area below the diagram. Simple, right? Yeah, I think it's very simple to understand. You have to try. Previously is the angle at point B. Now we consider the angle at point C. This is equal to the angle at point C. Consider from point A or from A. This is will be equal only this one, only triangle between B and C, only triangle between B and C. So the formulation only like this. Okay, after this slide, any question? And this is the basic for moment area theory. Yeah, this is only the angle. So how to find the deflection? This is the end of deflection. Let's see another example. Yeah, in this example, we can see another loading. In this case, the loading is moment pure bending. Yes, pure bending. It will produce pure bending because the load is moment bending with a similar uniform material and AI is constant. So what is the displacement of point B and C? Previous example is only about the angle. But now we consider the displacement. Yeah, the similar method we have to draw, we have to solve first. First of all, we have to solve the support of reaction. Then we have to draw the moment diagram under the beam. After we get the moment diagram, then we can solve the option. Yeah, the deflection equal with deflection at point B equal to T at B from point A as well as at point C. So next, then we can calculate by applying theorem 2. This is based on theorem 2. T B per A or equal deflection at point B is equal to the moment of the shaded area under the MI diagram, MAI diagram, which is computed about point B. Since this is the point where tensile deflection is to be determined, hence, thus, the formulation will be like this. This one is the um, moment area O per AI times L per 2. Moment area multiplied by L per 4. L per 4. Why L per 4? Because this is the center of gravity of the area. So here, this is the moment area, and this one is the uh, center of gravity of the area, center of gravity of the area. So this is, by this formulation, we can obtain the deflection at point B. Let's see deflection at point C. Uh, this is the moment of area at point C, and this one is uh, from A to C about point C. Yeah, likewise, with the similar uh, method for T, C per A, we must determine the moment of the area under the entire MI diagram. This one, from A to C, from A to C. A to C is A to C, from A to C. So the total is L times this one. Right? Then we have to multiply with the center of gravity of this area. Center of gravity is here. And so this is L per 2. L per 2. So the final formulation is like this one. This is how to get the deflection at point C. Point C is at the end of the beam. Point B in the middle of beam. Any question about this? Can you understand? Yeah, if there is no question, the next slide is about superposition, but I will not talk about this. Please just you can learn by yourself because we have no much time to. There are four under six methods to solve deflection, but we only have 4 weeks. So I will choose the most simple way or the most simple method to solve the deflection static structure, either determinate or indeterminate. Let me see the sample problem that we can solve with uh, moment area method. This is the moment function. This is the indeterminate, how to solve indeterminate problem by integration method. Okay, so I will make some rewind for indeterminate. For determinate problem, I have delivered two methods. The first one is double integration, and the second way is moment area method. Moment area method. Based on two methods, also you can solve indeterminate problem. Indeterminate problem. But before we proceed to indeterminate problem, we have to understand what is the difference between determinate, static determinate, and static indeterminate. Static determinate and static indeterminate. Okay, I will show you from the statics course. Yeah, you already learned last semester. What is the difference between determinate and indeterminate? Maybe we can find here. This is how you find the moment area. You already learned in the statics. So, yeah, this is the closer slide to explain about determinate problem or determinacy. Yeah, there are two powers uh, of the structure uh, become determinate or indeterminate. The first cause is redundant constraint. Redundant. You see in this case, this is overhanging beam with two support at point B and C, and that point A, uh, the support type is fixed support. Fixed. So if you draw the free body diagram, you can see so many uh, reaction here. So many reactions with only two type of loading: transversal load and uh, moment bending. Moment bending. It means that this structure has abandoned constraint. Too many support. In my term, I said this structure had too many support. So we call this indeterminate or indeterminate structure because constraint or too many. And then the second type is improper constraint. Improper constraint or too less support. Too less. Also, it will cause indeterminate problem. There are two types, concurrent at a point, and another type is reactive forces are all parallel. You see, at concurrent at a point, what is the problem? How the structure become indeterminate. Support types. The support type. You can change at point A only a roller. That's this structure become determinate problem, not indeterminate. But in this case, we see that the support at point A is not roller but pin. Is the pin type of support. So it has two reactions. So it will create improper constraint. And the second example is reactive forces. You see the problem is has slope concentrated force, but the support only vertical reaction support. Miss or can have vertical horizontal support. Horizontal support is missing. Horizontal support is missing. So it will cause as well indeterminate problem. Indeterminate. Okay, do you understand this? So divine. What causes the indeterminate problem or structure? Graphite, too much support or too less support. Too much support or too less support. Yeah, let's we go back to the deflection problem. After you understand about what is indeterminate structure or indeterminate beam, then our question is how to solve the problem, how to find the angle and find the vertical deviation or maximum deflection of beam if the beam has indeterminate structure. For the beam with indeterminate structure, uh, we can solve the problem if we put another or one more formulation. Either the problem is too much support or too less support. Either the problem too much or too less. So the simple way is just we have to find one more formulation. We have to find one more formulation, then we can solve the problem. And the formulation you can get from the uh, deflection formulation. You can get from the deflection formulation. I have delivered two methods, double integration method and second way with common area methods. Common area method. So you can try, please attempt to try one more formulation to solve indeterminate problem. Let me see. Uh, yeah, this is the theory. This is the theory. Yeah, this one indeterminate beams using method of integration or double integration. So here we have to find another formulation, another uh, one more formulation. Let's see the implementation. Yeah, this is the example 12.17. Beam is subjected to the distributed loading zone. Determine direction at point A. AI is constant. Okay, the loading is distributed force, triangle type, and the question is determine the reaction at point A. For this case, say, can you say this is too much or too less support? This is too much or too less support? Anyone? Any idea? Any idea? This
Too much,
problem?
sir.
Yes. This is too much or too less?
Too much.
Too much. Yes. Very good. Yeah. This is too much support. That should be at point B, not fixed support. But you can use just pin. in support because the loading is vertical loading, even this is distributed force. Okay, so how we can solve this problem? In this case, we use the double integration. So all formulation based on double integration in defect at sound, a sound and the one coordinates x is needed. Okay, for context, will take it directly to the right since internal moment is easy to form. Yeah, this is from you can solve the problem from left to right or right to left as you like. But if the problem like this, the simple way, if we start from left to right, because the support in the right, support in the right. Then the first of all, you have to find support reaction, or directly you can start from the left to right. Yeah, this is the so here there are two sections, right? Please remember the section method to draw moment diagram or to find the integration formulation. This is the first one and the second one. Maybe you will confuse if I draw here. Yeah, we have to, this is the distributed load, we have to change become concentrated load. Then we have to apply two sections, AA and BB. So, as you see here, we have two sections. Then we can function, sorry, the internet connection after the call problem. Then this is the moment function, and then we can apply to get slope and elastic curve from the double integration into one by one. Then we can get the this is the slope of the sorry the deflection formulation. Deflection formulation. 1, 2, 3. We have three formulation. Yeah, because we already have three formulation. The three formulation is as list. Please, we have to find C1 and C2 first to solve or to get C1 and C2. You already learned last week. You can see here from the boundary condition, we can get C2 equal to 0 and C1 equal to this part. This is equal to C1. So this is the deflection where x equal to r, deflection is 0. Can you understand? This is x equal to r, deflection here is equal to 0. So this is 0, and then we can solve this. So C1 and C2 is solved or found. We see the result for A, Y, direction at B be determined from the equation of equilibrium. This is the final result. Yeah, the question is reaction at point B, reaction at point B. Even this is indeterminate problem, we can solve by put another more equation, more equation or formulation. I said before is formulation. But from uh, double integration, you already get two more formulations or two more equations. It is formulation. With two more equations between or beside sigma normal equal to 0. This is 1, 2, 3. So you can find the reaction at point A. You can find reaction at point A. Okay, can you understand this part? Any question? Yeah, I revise. To solve the indeterminate problem, the concept is find uh, as much as formulation. Find, try to find as much as formulation. Using the double integration method, we already have two more equation. Two more equation. The equation is this number one and this is number two. One and number two. Equation beside rigid or free body diagram. Beside rigid body equilibrium. This is rigid body equilibrium. Actually, this is number three formulation, number one, number two, and number three formulation. So you have three formulations, three equations to solve unknown is enough in indeterminate form. Okay, I will show you the this is the main 9 week is about the concept of the diffraction, and then 10 week uh, and also the double integration method. Then 10 week is double integration and moment area method. Yeah, for determinate problem, and 11 week is Castigliano. I will not discuss about the superposition or discontinuity because the time is uh, limited, very limited. You can learn by yourself. As I said before in the beginning of this lecture, today's lecture, that I will not focus uh, on how to solve, uh, on how to use the method of diffraction, but how you can solve the diffraction by the right procedure, not by uh, special method, not by special method, but with the right procedure. So now I will continue to moment area for indeterminate problem. Moment area for indeterminate problem. Discontinuity is this one. Yeah, this slide talk about moment area method for indeterminate problem or indeterminate structure. Yeah, the basic concept still similar. and we have to find as much as equation. We have to construct as much as equation, at least three equation coupled with the uh, rigid body equilibrium. Rigid body equilibrium. And you can read the procedure. Yeah, draw the first procedure is draw the MA for oil diagram. I think this is M for AI. M for AI diagram. Yeah, M for AI diagram. Subject to the tangent are represented as unknown. Simply the two moment area theorems to get the relationship between the tangent and elastic growth to meet condition of displacement and or slope at something. This is number of compatibility condition is equivalent to number of redundant. Yeah, to construct or to draw moment diagram, we can use another method. Maybe this is the simple way to construct the moment diagram. We can use method of superposition. Why? Because moment area theorems need calculation of both the area under the and the I diagram. The method of superposition can be used to combine spirit and I diagram each of the known nodes. That is the concept. Most loadings on beams are a combination of different loadings as well. Combination between concentrated moment bending and distributed load and inclined distributed load. So the typical moment diagram, see below, this is triangle, this rectangular, parabolic, and cubic curve. Yeah, superposition usually used to construct the moment area below the diagram. Moment area below the diagram. After you get the moment area, so you can use the theorem of moment area to solve the problem, either determinate or indeterminate. Yeah, like this, you can see in this slide. You can see in this slide. This is the problem with three types of loading: concentrated loads, moment, and one distributed loads. Distributed loads. So you can see we can separate the loads, become only distributed, only moment, and only concentrated load. So this very simple to get the moment area below the diagram. So after we combine all moment area, we can get the combination of the moment area below the diagram. But this is the similar example, yes, similar problem, I think. From the complex one, we can derive into three separate loadings. Three separate loadings. Okay, then uh, moment area to solve the problem for indeterminate one. This case is indeterminate one. How we can apply moment area to solve this problem? First of all, we have to draw the, the diagram M per AI. Yeah, M per AI, not M A per I, but M per AI diagram. After we get the diagram, then you can use the construct equation of formulation. Yeah, because this is another moment at point C, so the diagram will be like this. This is because the moment, and this one because the concentrated load. Sin delta A, B, C equal to 0. So you can see here A, B, and C equal to 0. The tangential deviation shown must be proportional. A, B, C equal half to KAC. Okay? Then you can calculate using the moment area method. How to use that one? This is not the angle, but this is the deflation. So we have to multiply between the uh, center of gravity, and the moment area method. Moment area. TBC. Which one TBC? B and C here. So you can see 1, 2, 3. 1, 2, 3 area. 1, 2, 3 moment of area. But in this another side is only 2, 1 and 2 area. So here you can see 1, 2, 3 and A consider 2 or refer to point C only 2 area. Yeah, after we get the equation for B and A, then start to put it into equation 1. This is equation 1. K upon B equal of then KA from C. So this is the basic equation. Let's see. Yeah, this is proportional if there is no support at point A and B. So this formulation, you can understand this formulation if you can imagine that point A and B without any support. So the vertical deflection or vertical deviation equal with the equation y. Then we can get the reaction at point B. Then this is another equation, another problem. Yeah, so fusely is considered from point C. Then how if we consider from point A? So it should be same. It should be similar. We have to get the same answer. Okay, that's it. The slide. The next one is about superposition. Okay, as I said before, I will not discuss about the superposition. You can read by yourself because it is not my focus in this class. That's it, the explanation for moment area method and double integration for determinate and indeterminate problem. Any question?
Sir, excuse me,
Yes.
sir.
Hmm.
I'm sorry I didn't fill the presence code earlier. Can you please open it again? I'm sorry, sir.
Which one?
The presence code. I'm sorry I didn't.
Lesson? This one or this one? The, the appendix code, yeah, it's code only lasts for 15 minutes. Actually, I think you can ask to your friend about the appendix code. And now, more than 15 minutes. Okay, I will continue to next material about Castigliano. But before proceed to Castigliano methods, this is a different concept compared to integration method. Uh, yeah, I need pause maybe 10 minutes. Yeah, we continue in 11:22. Okay, we pause the lecture. I pause the lecture for 10 minutes.
Okay, sir.
The direction of transversal loading, and the last one is for bending moment or bending loading. Yeah, this is the transverse here. This lab is being distinguished between transverse and direct shear. Transverse shear and direct shear. That is one. Yeah. After we get the state energy formulation, and this is some simple problem, you can take it later. It is the sample just now to look at the strain energy, total strain energy. And using the strain energy, we can use that to find the deflection and also the angle, deflection and the angle. And in this case, we need the theorem, and the theorem is introduced by Castigliano, or Mr. Castigliano. So we call this as Castigliano's theorem. There are two theorems. The first one that regarding with the displacement, and the second one regarding with the angle or rotational displacement. So for the displacement or vertical displacement equal to derivative of strain energy to that forms, or equal to partial derivative of total strain energy with respect to that force. With respect to that force. And for the rotation or angle, first energy with respect to the moment. With respect to the moment. So here, deflection is respect to the force. The angle is equal to the moment. So how to implement this theorem? Yeah, I already introduced to you to theorem, the moment, barrier theorem, there are two parts, and plastic nanotheorem also two parts. Yeah, this is the implementation of plastic Liano's theorem. Yeah, this is the simple example. Okay, one overhanging beam with one concentrated force. The line is L. The diffraction mass multiplication will be y. Find the maximum deflection or y max using Castigliano. Yeah, the first one, yeah, the procedure, we have to find the total energy, strain energy, total strain energy. Then we have to do a partial derivative respect to the force to get maximum deflection. That is the first step. The second step, this is the total caused by the, as you see here, this is the traverse. So I will get uh, traverse and moment, right? Traverse and moment. So there are two parts. This is direction, and this one is force. That's me check. Yeah. Okay. This one is direction, and person from person. Sorry. This one. Moment. Time. And this one is moment. Yeah, this M, this concept M equal to X times okay, and and direction. So after we get the total strain energy, then we do or we derive into respect to the force, not respect to the moment. But even there are two parts, beam, uh, bending, and force, direction. So to get a maximum deflection on the respect to force, not move. Then finally you will get this magnitude. Yeah, this is the basic concept. Before I continue to how to get deflection on the any point. Any question about this? Any question about the concept of the Castiglione method? Yeah, let's see another example from another slide. This is Castiglione law as well. Strain energy. Yeah, this is the first theorem respect to the force, and this one should remember angle of rotational displacement. So the vector of rotational displacement respect to the moment. Yeah, exactly similar. That this is one example. Okay, you can repeat later. I get to previous slide is about how if we want to use Castiglione theorem to find any deflection at any point, which is with have no another no have no any or is the concept utilizing fictitious force. Castiglione method can be used to find a deflection at any point, even if there is no force applied at the point. The concept or the procedure just we put fictitious force, fictitious force at point we need we need to observe. Then we calculate the total energy, total state energy, including the fictitious force. And follow the procedure as usual. Follow the procedure as usual. After the derivation is taken, after the derivative process is completed, so we can set the derivative to q equal to 0. We see the implementation of this concept. I will also to this one. Sample on form state 10. Using Castiglione method determine the reflection at point force and B without any force. Without any force. Without the force at the steps. So this similar material, uniform but different cross-sectional area. Different cross-sectional area. So it will create or it will give different moment of inertia. Different moment of inertia. Okay, first we have to put fictitious force at point B, namely Q. Yeah, namely Q. Just we call this as Q force. Yeah, we can omit to find the ground reaction or sub of reaction. yeah, just we try to find the bending moment. Find the bending moment from 0 to L. From 0 to L. So the bending moment is going to minus x and x, and then yeah, this is the reduction derivative of strain energy per yeah, derivative respect to the. So the potential will be like this. Then by substituting the equation 1 to equation 2, when the I, because it's the different cross-sectional area. So if we suppose we consider I1 equal to I, so the for I2 equal to 2I1. This is one 0 to I over 2, and for I equal to 2I1 from 0 per 200. So I can have 200. So you can because it is uniform material, A, you can exclude from formulation, but the E is still inside the derivative, partial derivative, and finally we will get this formulation. This is from 0 over 2 over 2 to N. Yeah, this one is at 1A and 1B. No, nothing difference, nothing special, because 1A the first is exists, but at 1B is no forms. For that 1B, we have to put one more 15 forms, and the access page forms still remains exists. So the moment the person will equation three, if you still confused how to get the moment equation, so my assumption is you want to master statics first, uh, so you need to remind or to study again about the statics before complete this course. After we get the formulation completed, at the moment, like in question number 3, then we can learn partial derivative aspect and from 0 to there are two parts from 0 to 2 everything to uh, 0 to other 2, we just need this equation, but the derivative still respect to the q, so equal to 0, right? And to we have to use another part of the equation, and this is respect to the q, so that is not 0. Then from 0 to 10, we can get after partial derivative, then we can get this final solution. So the detection of point B again is positive, but less than or smaller than special infection or point A, sorry, equal to 3 per 16. 3 per 16, and here factor per 96. So this is small. But this is makes sense. Action point program. Yeah, this is 1+, no? Yep. Before I continue, we can make a shortcut for the procedure of cascade method. There is another shortcut. Uh, so we don't need to find strain energy to calculate deflection. And this is the shortcut. For cases requiring integration of strain energy equation, it is more efficient to obtain the deflection directly without explicitly finding strain energy. Yeah, after you can apply this shortcut method after you understand more about the strain energy. If you don't understand, still not understand about strain energy, please do not use this shortcut method. Then the shortcut is we can move the partial derivative inside the integral. So the example we try here, it is the shortcut method. So why you see the equation like this one? This is the shortcut. Here we do not need to calculate strain energy. Just uh, we need to find the moment bending equation. Moment bending equation. This depend on the problem. But in the problem for deflection of the beam, vertical deflection, yeah, we need the moment equation. But in the case of buckling, buckling is a vertical beam getting but maybe another loaded method. Yeah, we can get. Yeah, for example, in the bending moment, like this, then this is the concept, the first concept. Then we move inside the integral for moment. Then we retract the derivative parts. Then you can uh, get this equation. And finally, this is the simple methods. So you don't need to calculate the strain energy first, then derive partial derivative to force or moment to get deflection and lateral. We can use this direct formulation. This is the direct or shortcut formulation to get deflection. Okay. Yeah, especially this method have full response set will be set to zero after the derivative is taken. Yeah, now the loading time, expansion and compression, carefully. So and another term is torsion and bending. Compression, torsion. So you can use this this formulation, this equation directly, we can calculate strain energy or total strain energy force in the implementation of plastic Liano theory. Okay, that's it for plastic Liano. Yeah, it was more and more practices. For today, let's cover two which material. Lecture today is cover which material, suppose for last week and this week. Okay, for last week and this week. Okay. So if you taken this class, but I mean for the attendance, uh, I consider 2 day attendance equal with last week attendance. But actually for last week, I actually already put your attendance is okay. The, the attendance is already for the 1 month, and that will be 1, 2, 3. So it should be six practices, one for double integration, determinate and indeterminate. Number 3 and 4 is for determinate. And number 5 and indeterminate. Okay, sorry. For Castigliano, actually we can, for indeterminate, I will deliver or explain next week. But for Castigliano, I will give the example for with 50 years force and return 50 years force. Okay, that's it. I will try to check out the practices. Maybe tonight, maybe tonight, I go for tonight. So if it's ready, I will announce in the Teams group. I will announce in the Teams group. Okay, that's it. Any question? Okay, no question. If no question, I will post my lecture and we see you again next week at the same time to discuss or to learn together about the Castigliano or indeterminate problem. Okay, see you next week.